Hey guys, hopefully you are enjoying your day off from lecture, but I'm still holding you responsible for watching this video. Kind of an intro to chapter 9 before Monday, and we can kind of get a head start so we can finish quickly and get to chapter 10. So, chapter 9 is all about acids, bases, and salts. You should be able to find the lecture online. I have not printed it out yet, but I will have it printed for you on Monday. Please make sure that you are looking online to find this lecture. It is already up, so you should be able to find it. So chapter 9 is on acids, bases, and salts. First slide, we're talking about acids. What is an acid? Some properties of acids. First of all, we think they taste sour. So hopefully you haven't been tasting acids every time or any time we've used acids in the lab, but when we think of our real world acids, we think they taste sour. So some things that you should be associating with acids then are things like lemons, lemon juice, maybe oranges or limes, maybe vinegar. Vinegar is definitely an acid, so we think that acids in our lives taste sour. We can also think in a more gross way. If you've ever thrown up in your mouth, you know that that is a nasty sour taste, and that is because your stomach acid. So when we think of stomach acid, again, made of an acid. When we think of acids in terms of chemistry and in the lab, we think that they turn litmus red. Now, litmus paper is this special indicator paper that tells us whether a substance, a liquid substance usually, is an acid or a base. When we take this litmus paper and dip it into acids, you guessed it, it turns red. So, acids also react with active metals to release hydrogen gas. For those of you that remember Chem 110, one of the first labs that you ever did was when you took iron. You took solid iron, you added some hydrochloric acid, and you got bubbles. And on this first slide it says reacts with active metals to release hydrogen gas. So those bubbles were most likely filled with hydrogen gas. Now there's other stuff in there, but that's kind of cool to think about, that iron reacts with hydrochloric acid to produce hydrogen gas. Acids, the last little tidbit of information, is that they react with bases to form water and a salt. Very interesting. So, when I think now of bases, moving on to the next slide, when I think of bases as the anti-acid. So bases I consider again to be the anti-acid. Bases taste bitter. Bases taste bitter. Again, you shouldn't be tasting any kind of base in lab. Sodium hydroxide is an example of a base, so hopefully you've not been tasting sodium hydroxide. Bases turn litmus blue. So if you take litmus paper, put it in acid, it turns red. You take it, put it in base, it turns blue. Bases feel slippery. Now that's a weird thing to think about, but bases, when we think of acids, we think of burning, corrosive. They hurt our skin if it gets on our skin, but so do bases actually. When we think of bases, they get on our skin and it burns just as much as acid does. We may not feel the burn until later, but it does burn your skin. Now, bases react just like acids. It says they react with acids to form water and a salt. Acids react with bases to form water and a salt. Bases react with acids to form water and a salt. So, a couple of pictures just to think about for you. So the next slide is showing on the very left a container of vitamin C, a container of vinegar, a lemon, an orange, and a bottle of aspirin. If you haven't guessed it so far, that is showing you acids. Meanwhile, in the center, I have drain cleaner, I have milk of magnesia, baking soda, and ammonia. So the Phillips milk of magnesia, that's also known as something like an anti-acid or an antacid, something you use when you've got some kind of acid reflux or heartburn type of thing. So those are bases or anti-acids. On the very right, you have this thing called True Blue aluminum sulfate, kosher salt. And there's a bottle that you can't see in the picture, a bottle of water in the background, and that's what we call neutral. Neutral is halfway between being an acid and halfway between being a base. We say neutral is water and salts. So I'll try to separate this. Again, when I think of neutral, I don't think of it as being an acid. I don't think of it as being a base. I think of things like water or salts. In this case, we talk about salts, and the first thing you think of is sodium chloride, but I'm going to give you a better definition for what a salt actually is when we get there. So, one thing to note now, just as a refresher of what happens when I add any kind of ionic compound in water, I remember that if I add sodium chloride or an ionic compound like sodium hydroxide, or if I add something, say, like, I don't know, sodium oxide, we think that in water I've got my cation and my anion, and in water they break apart. So in water, I say that ionic substances ionize in water, again, to form things like aqueous ions. So aqueous ions, chloride minus aqueous. When I have an ionic compound in water, it dissociates and forms my positive charged ion floating around in water and my negatively charged ion floating around in water. So, now, that should be in the back of our minds as we talk about acids and bases for now. So we have a couple of definitions for acids and bases. The first definition we're going to talk about, other than these experimental definitions that we just covered, for acids, we're going to talk about the Arrhenius theory first. And there are, again, a couple of theories about acids and bases, and the first one we're going to cover is the Arrhenius theory. The Arrhenius theory tells me that a molecular substance that ionizes in aqueous solution to form hydrogen ions, H+ ions, is an acid. So, let's read that one more time. A molecular substance, so I'll call this, I guess, A for acid. A molecule that ionizes in aqueous solution, so ionizes meaning it must turn into some A plus or minus, again, to form an ion in aqueous solution. Okay, so it must be some, aqueous, I guess. To form hydrogen ions. Okay, so that means that I must also form H+, aqueous. So again, the Arrhenius theory tells me that a molecular substance that ionizes in aqueous solution to form hydrogen ions in solution, okay, that means that I must have had hydrogen attached to whatever this thing is here, HA, forming H+, which then means that whatever I have left that ionized must be some A-. So this kind of looks similar to when I have sodium chloride. Again, when I have sodium chloride, NaCl, I have sodium plus break off and Cl minus break off, similar to my Arrhenius theory for acids, that my acid dissociates into H+ and A-. Now that A-, who cares what it is? That's not part of the Arrhenius theory. All the Arrhenius theory says is that my acid is some molecule that in water breaks apart and produces H+. That's the big key here. So, one acid that we should be pretty familiar with is hydrochloric acid. According to the Arrhenius theory, what hydrochloric acid does is produces, again, H+. And that means that it must also produce Cl-. Again, when this thing breaks apart, I would produce H+ and Cl-. Now, bases. Bases, when I think of bases, the Arrhenius theory tells me that my bases, instead of breaking apart to form H+, my bases, whatever it is, I'll call it B, is going to break apart to form OH- aqueous. So whatever that is that I have attached, that means that I must have started with hydroxide. So whatever I started with is supposed to break apart to form hydroxide in water, and that means what I've got left over is some B+ aqueous. Whatever that stuff is, again, we're just saying B is whatever is attached to my hydroxide. So a perfect example of an Arrhenius base, I say, is sodium hydroxide. And I say that sodium hydroxide in water is going to break apart again to form OH- and Na+. And that's a perfect example of my Arrhenius base, something that in water breaks apart to form OH and something else. So, now, the problem with the Arrhenius theory, there are a couple of problems with this theory that we've talked about. First of all, the problem with this theory is not all bases break apart to form hydroxide. So, if I look at ammonia, NH3, I can say, okay, NH3, according to Arrhenius, again, if NH3 is a base, which I have tested, I promise you ammonia is a base, it should produce hydroxide. There's something wrong here. I started with nitrogen and hydrogen, and now I'm ending with oxygen and hydrogen. That doesn't really make much sense at all. So this is a limitation to my Arrhenius theory. This doesn't make any sense. Another limitation to the Arrhenius theory is that when I think about my solutions of acids, I look here and I'm like, okay, if I reach into my bucket of solution here, I should find A minus in solution. I should be able to reach in and grab A minus out. I should also be able to reach in and grab H plus out. The problem is we have tried and tried and tried and we have never found H plus. What we do find instead is we find something called H3O plus or hydronium. This is my hydronium ion. My hydronium ion, H3O plus, looks really similar, familiar to us. It looks kind of like water. So what I can think of here then is that my acids, my HA, whatever that A is, I can think that it's dissociating into A minus and H plus, but that H plus is meeting water. When H plus meets water, I form H3O plus. So another way that I can write this reaction then is HA and water produces A minus and H3O plus. Now, what I can think of here is I can think of H3O plus. If I'm talking about H3O plus, I can consider it the exact same thing as H plus because, again, if I'm trying to measure the amount of H plus, I'm really going to be looking for H3O plus because that's what I will find in solution. If I make one of these, water attacks it, grabs it to form H3O plus. So now we've come up with another theory instead because, again, that weird thing with ammonia and this weird thing about how H plus, we can't find it. We've come up with a new theory called the Bronsted-Lowry theory. The Bronsted-Lowry theory is pretty simple and defines acids and bases in 2 words. We say acids are proton donors. So the Arrhenius theory was kind of ignoring water for the most part, so what we say now is that my acid HA reacts with water to produce H3O plus and A minus. Now, what is a proton? A proton donor. Acids are a proton donor. When I think of a proton, I think of this positive charge, and what did my acid really donate? From here to there, it seemed to have donated an H plus. Now let's look at what H plus is. If I just look at H neutral, a neutral atom of hydrogen, I have 1 proton, 1 electron, and however many number of neutrons. The most common number of neutrons is 0. So I'm looking at a normal neutral atom of hydrogen. When I have a proton, H plus, a proton, H plus is when I take away an electron and I'm left with nothing but a proton. So when I talk about proton donors, all I'm really talking about is H plus. I say proton is the same thing as H plus. Again, when I say proton donor, what I'm actually saying is that an acid right here is an H plus donor. It's giving up an H plus. Now, who's taking that H plus? In this situation, it kind of looks like water is taking that H plus. So again, I'm going to call this thing my acid. My acid because it is donating a proton. Now, bases. The definition, the Bronsted-Lowry definition for bases is pretty simple too. Proton acceptors. So I think acid donates, acid donates, acid donates, acid donates. Acids donate protons, bases accept protons. So when I think of my base, say something like ammonia. When I think ammonia and water, we're just going to use water. Ammonia and water. If I say that ammonia acts as a base, I'm going to say that it's going to accept a proton, meaning in the end, I will form NH4+. And what's left of water? Well, nothing but hydroxide. Now that's kind of interesting. We said that Arrhenius was wrong. Arrhenius, we said, told us that bases are things that break apart in water to form hydroxide, and I mean, ammonia did not break apart to form hydroxide, but it did form hydroxide in water. It's just that Arrhenius had kind of been ignoring the role that water plays in these acid-base reactions. So now, again, I see that ammonia is acting as a base because it accepts a proton from water to form NH4+, don't forget your charges, and water therefore gives up a proton to form hydroxide. So what I can think about then is that H3O+ is formed when adding acid to water. I can think that hydroxide is formed when adding base to water. Base to water. Kind of interesting to think about. So an acid donates protons, and when we think of an acid reacting with water, I think of an acid donating a proton to water to form H3O+. When I think of a base in water, I think of a base accepting a proton from water to form hydroxide. Now, whatever else is formed doesn't matter, but a base will form hydroxide in water. And again, that goes back to our Arrhenius definition. Even though Arrhenius was ignoring the water, he still was technically correct that a base in water produces hydroxide. Kind of interesting. All right, so we will work on this. I'll do a little quick review, maybe two or 3 minutes on Monday, but I'm hoping you guys watch the entire video by then, and you'll have a good idea by the time we start on Monday. Have a good Thanksgiving.